All right. Greetings, everybody. My name is Lazaros Moysis. I am a postdoctoral researcher at the Laboratory of Nonlinear Systems, Circuits and Complexity Physics Department at Aristotle University, which is in Thessaloniki, which is the second bigger city here in Greece. So, today I'm going to discuss about a chaotic path planning method for 3D area coverage using modified logistic map and the Modulo Tactic. Pretty big title, do not worry, it's a very simple approach. So, let's begin. I'm going to discuss about three main things. Okay, first I'm going to discuss about chaotic systems. Then I'm going to discuss about the application of chaotic systems to path planning in 3D areas for UAVs and 2D areas for simply autonomous robotic agents. And third, I'm going to discuss about future research directions for our work. So, let's begin with a very simple definition of chaotic systems. You all have heard the term, you may not understand its actual mathematical or physical definition. Now, by chaotic systems, we generally refer to deterministic systems that have extreme sensitivity to initial conditions and parameter values. So, first of all, we do not talk about stochastic systems, okay? Chaotic systems are generally simple deterministic systems. And the extreme sensitivity to initial conditions means that even if I change even the slightest, the initial condition of a system or a parameter of a system, the solution is going to be completely different. Okay, let me show you that with a simple animation. So let's do, okay, we have three pendulums starting from almost identical initial conditions, and you see what happens. Within 2 or 3 seconds, the trajectories of the pendulums diverge. See it again? All right, from the second, and then the solutions are completely different. This is an indication of chaotic behavior. Okay, let's see a second example here. Let's start from the beginning. I have two balls bouncing on a circular area. They start from almost identical initial conditions, but you see that after 1, 2nd, 3rd, after the 4th bounce, their solutions are completely different. Okay, so these simple animations are simple indications of a system behaving in a chaotic fashion. Okay, even the slightest change will give a completely different solution trajectory. This is what we talk about when we discuss chaotic systems. Here in our work, we are going to use a very simple discrete time chaotic system. So it is an iterative formula given by this very simple term. As you can see, there are only two terms here. Beta is a parameter. And here, for example, I plot the solution where the beta parameter is 0.5. And you see two different solutions. One has initial condition x0, 0.1, and the second one has initial condition x0, 0.1 plus 10 to the minus 15. As you can understand, the difference is very small, but as I plot the solution of the system, you will see that after the 50th iteration or so, the two trajectories begin to diverge, and up to the 0.70, they are actually completely different. Although, for some time the solution looks the same, in due time the solutions completely diverge. So this phenomenon you might have heard in popular culture as the butterfly effect. Okay, even the slightest change in due time will give you a completely different trajectory, or will have, if you like, catastrophic consequences to the system. So this here is a simple chaotic system that we are going to use. Now, from a mathematical standpoint, what tools do we have to study chaos? One simple tool is the bifurcation diagram. This indicates something very simple. For different parameter values, where do the actual values of the map x0, x1, x2, x3, x4, where do they lie? For example, here, if you take a look, for parameter value beta equals 10, I can see that the parameter values lie between minus 20 and 20. For beta equals 20, the values lie between minus 40 and 40. So I have a clear indication of where do the values of the system lie, where values do they take. The second tool is the Lyapunov exponent, a mathematical tool. Actually, what it tells us is if the system trajectories diverge from each other or not. So simple as that. If the Lyapunov exponent is positive, the system is chaotic. So here we see that for all parameter values, 25, 30, 35, 1000, The Lyapunov exponent is always positive, so the system here is actually completely chaotic. This is what we want to use. Now, specific application. Chaotic path planning. What is it? How can we use it? The aim here is this. We need to use the values of the chaotic system we showed previously, the ones I plot here, and use them somehow to design a navigation strategy for a UAV or a simple ground vehicle in a way so that we design a motion that is, first of all, unpredictable. That's why we use a chaotic system, because it is very hard to predict. And it looks random, it looks unsuspicious to an outsider, especially for camouflaged robots. But although it looks random, at the same time, and this is very important, it guarantees efficient area exploration and area coverage. So if I want to use that to explore an area, the motion may look as if it's happening, randomly, but we know that at the same time, this robot or UAV will give us a complete area coverage over time. And that's why we call it chaotic path planning, okay? This sort of path planning has been reported in the literature to be used in domestic applications, like floor cleaning, for example, in firefighting, in area exploration, in patrolling robots or UAVs, and for example, in surveillance cameras. So there are a lot of applications related to security, exploration, etc., or chaotic path planning. So how are we going to do it? How can we use the values of the discrete time map x0, x1, x2, x3, x4, etc. to generate some form of chaotic motion commands, chaotic navigation strategy? Here we use a very simple technique. The technique we are going to use is xi modulo 26, and from that we take the integer part. Okay, so we have in each iteration generate a number between 0, 1, 2, 3, 4, 5, and 25. Based on these results, I design a simple discrete navigation strategy given here, and I hope you can understand it. It's actually a collection of 25 different direction commands. Forward, left, right, backward, back left, left, left up. Up, right, right and up and back, So we have a collection of simply discrete directions that a robot or a UAV can follow. Okay, this is what I'm going to use to design a strategy for a UAV that moves chaotically. Because as you can understand, since we designed that using the values of a chaotic system, the motion commands generated have, chaotic motion, They are generated from a chaotic system, so they are totally unpredictable. Here, this motion these motion commands I computed for, I think, 2 million values or 2 billion, and we see that we have a uniform histogram. So this is an expectation that the simulation is going to be very, very good. So let's see how the robot moves. I hope the frames are good. So let's see it. They're a bit fast, but doesn't matter. You see that as the robot moves, it explores little by little the given area. I'm going to strafe it a little bit so you can see that the area is pretty much covered sufficiently. I think this is 15,000 steps, if I'm not mistaken. And here on the right, you will see a color-coded graph of that coverage, where you can actually plot by color the number of visits in each area. So you can see that, there are some places that I have like 10, maybe 5, 7, or even 12 visits to previous spots, which you can always see here again. So for example, here I have a simulation for 10,000 and 150,000 steps. You will see that the area coverage increases, but as the number of steps increases, we have some form of, visits to previous cells. So you can see here that some places, some cells are revisited 1, 2, 3, 10, 20, 15 times, which is to be expected, of course, since we don't apply any sort of optimization technique here. So one way to improve this is to use some form of chaotic inverse pheromone technique. Here, what we do is we simply see this graph here. What we do in every step of the way, we simply keep in our memory, the last F cells that we have visited. So, for example, here, when we are about to perform a new motion, we only consider steps that have not been revisited the last F times. So, in this motion, we only accept motions here, 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 here. So, these two are rejected. This way, we can apply sort of, avoidance of backtracking, so we can greatly improve the performance. So upon doing specific simulations for an area of size 50 by 50 by 50, I see that as the number of iterations increases, we actually manage to acquire complete area coverage. So you see that the coverage here almost gets to 100%. So we have complete coverage. Using the pheromone, I see that I don't have a lot of improvement. You see they're pretty close, even if I use one level of pheromone, 5, 10, 15, or even more. So the improvement in coverage is not very much. So it's like 1 or 2%. But still, we use pheromone because it helps us avoid backtracking here. Okay, so we avoid movements to previous visited cells. So it's very important to design a very smooth motion here. So we can see indeed that the uh, coverage goes to 100%. And also here I compute the mean visits per visited cells, and I see that linearly as the number of iterations increases, I have some medium, revisit to previous cells, which is to be expected. Now, of course, as you can understand, this motion can easily be applied to 2D motion. So instead of having a UAV, you can have a UAV with a fixed altitude, okay, or you can have a ground vehicle exploring a ground area. To do that, we simply change the modulo 26 to modulo 8. So as you can understand, we have 1, 2, 3, 4, 5, 6, 7, 8 different directions. Up, left, left, right, back, backwards, back left, back right, etc. So here, let me show you the simulation so you can understand how the motion performs. We see that the robot moves on exploring a given area. All right, very nice. And on your right, you can see that I have again a color-coded graph, which shows me that the number of visits to previous cells at some parts can be significantly increased, So for example, I have some areas here that I revisit more than 10 times. Again, it is expected because the method here works chaotically and we don't apply any sort of optimization. Now here, of course, if I am to study coverage, I see that in contrast to the 3D case, here the use of pheromone gives a very good improvement in performance. So, of course, as the number of steps increases, I can manage to achieve complete coverage of a given area. But here we can see that if I use a pheromone level of 1, 4, 8, or 12, or even more, I can manage to achieve in some cases even 8 or even 9% improvement in coverage. So in the 2D case, the use of pheromone is much more useful. And again, we have some linear increase in the number of visits to previous cells. But again, the pheromone here helps improve the previous visits to previous cells. So it works much, much better, than in the 3D case. Here, okay, I see one problem that we have to solve, as I told you, is the fact that, since we have discrete motion commands, so the commands are, up, down, left, up, right, up, left, etc. So they are discrete. When I want to apply it in a real scenario, I want to have, a much smoother motion. So you don't, I don't want to move in grids, but, make the motion a bit smoother. And to do so, I apply B-splines. You are, I assume, familiar with them. They are very easy to design and control in the computer. And they help make the motion smoother. So you can see here that both in the 3D and the 2D case, if you look at the zoom-in pictures, it is very easy to design, a much smoother motion for the robot or UAV to follow, which is probably going to be expected and, a huge problem to solve when considering implementations. So overall, what did we do? We designed the motion control for a UAV or a ground vehicle that can move chaotically and also manage to look, unsuspicious, but also at the same time explore a given area. And we saw that we managed to have very good coverage results, despite the fact that we didn't apply any sort of optimization. So this is a blind chaotic technique, if you like. And I'm really happy to say that this technique and this paper can be greatly, greatly improved and moved towards many, many different research directions. And I'm sure we're going to have much more many extensions of the results presented here. So one thing that we are really interested about is to sort of optimize this technique to achieve faster coverage. And I'm very happy to say we already have some preliminary results here. We sort of apply a local optimization technique to make the robot still move chaotically, but at the same time avoid many revisits to previous cells. And we have managed to get a much, much higher coverage rate and much faster coverage rate. Of course, we have, we are able to design many, many different intelligent chaotic techniques to use in chaotic motion. Here, for example, we use the modulo technique, the modulo operator. There are many different options. We need to design them, compare them, see which one is better. So many new directions of research here. We have, of course, to solve the problem of online generation of the smooth curve. Here, as you see, I applied B-splines to make the curve smoother, but also, let's make this larger. We can use different techniques, and in implementation cases, we may have to discuss how exactly we're going to design the B-spline, especially if the motion becomes, is generated in real time. This is very important because here I did it offline on my computer, but in online real time, you may have some issues and to solve. Of course, we need to discuss the application of multiple UAVs. Here we discussed only one robot, but what happens if we have 2 or 3 or 4 UAVs or ground vehicles? Can they explore the given area at the same time, not collide and collaborate to give a faster, exploration? Surely you can do that. It's a very important aspect. We can discuss that and research this in the future. And of course, we are very interested in the practical experimentation and the implementation of this design. Okay, we are mostly mathematicians and physicists, but we're really interested in seeing how can we implement this design, this chaotic path planning in a practical design with a real time, with a real UAV, and see how we compare theory and practice. There's going to definitely be a gap here, in bridging the theory and practice together, and see, energy efficiency of the UAV, how well does the algorithm perform. These are huge topics of research interest. There is a lot of applications to be done here. I mean, there is a huge amount of practical applications here, and we're really interested in that. As a closing remark, I need to say that me, along with Professor Volos, we have an upcoming special issue in electronics, if you allow me to say that we have about the field of studies, recent advances in chaotic systems and their security applications. And of course, path planning falls within that category. So if everyone is interested, feel free to contact us for more details. And I'm going to close by saying that I really appreciate your time. I hope you are all healthy at this weird time. This is who we are. I will be very happy to receive emails, questions, everything about it. Feel free to contact me. Stay safe. Thank you very much for your time. How do we pause this?